hello everybody. My name is Hannes Marien from Ghent University, as just stated, and this work was done in collaboration with the University of Naples, Federico II. So I'm happy to present to you Comprint, which is an image forgery detection and localization method, so to see if parts of an image are real or fake. Let's see if... Yeah, so as we all know, manipulating images and videos can be quite easy and fun. For example, using a website such as FaceHub, we can create a realistic face swap in just a few seconds and for free. So for example, here, we have the face of Captain Jack Sparrow of Pirates of the Caribbean, and we can simply change it to the face of somebody else, and we get quite realistic results very easily. But apart from these fun applications, we also have more dangerous applications, as stated before in the keynote. We have a deepfake video of a president, and this can have severe consequences if they are publicly saying something that they have actually never said before, or they have ever actually said in real life. So there's a need for countermeasures, and that's where our proposed method comes in. So we want to do forgery localization and detection. And here it is important to know the difference between localization and detection. So if we have an image under investigation, we can transform that into a heat map, a pixel level heat map that states for every pixel the probability or the likelihood that that pixel was forged. And then we do localization. On the other hand, we have detection, and that is making a single image level decision whether the image is real or fake. So let's first look at some related work that was used to get inspiration for the proposed Comprint method. So on the one hand, we have conventional methods that are typically a little bit older. They are based on handcrafted models. And this is in contrast to the newer deep learning methods that are more data-driven. And these conventional methods, often they do not generalize well yet to in the wild circumstances. They are performing quite good for their for the assumptions that they were made for, but they could still be better in generalization. Also in robustness to post-processing, these are not perfect yet. And one example of such methods is those that are based on the JPEG compression artifacts. So let's dig a bit deeper into that. When we have a compressed image on the internet and we edit it, then we usually recompress that image before putting it again on the internet. And then the thing there is, in this forged image, there is we can separate two regions. One of them is the edited region, which only underwent a recompression, and the unedited region underwent double compression. So this difference in compression, single and double compression, is often used by conventional methods to detect a forgery. And similarly, we can have in a splicing, if we have two compressed images that we want to combine, both of them underwent some compression, then we do a recompression and we get the forged image. And also here we get two regions in the image that both have underwent a different compression. And this is often used by existing methods. And this is also used in the Comprint method that we are proposing. So again, so we have the conventional methods, and we also have the deep learning methods. And in deep learning, we can basically separate them in two classes based on their training data. If they use forged images in the training, or if they only use pristine images. And when they use forged images, they typically learn some traces of forgery. But the thing there is that it's hard to include all types of forgeries in the training data because some of them don't even exist yet. So they often do not generalize well in the wild, although the results have shown that they can be quite robust to post-processing. So on the other hand, we have the pristine images, and there we will basically model some normal behavior, and we're looking for some anomalies in that normal behavior to detect forgeries. And the thing here is that these generalize often better to forgeries because we are not dependent on those that are seen in the training data, but the robustness to post-processing can still be improved. And one noticeable example here is the noise print method that was made by the University of Naples, and that's how we got into touch to do this work together. And in the noise print method, basically what we're doing is we're exploiting the camera-specific noise. So when a camera makes an image, there's a bunch of noise in there that is unique to the camera, as most of you will already know. For example, there is some noise unique to the sensor. And NoisePrint is basically exploiting this and is creating a camera model fingerprint from an image. So when we have an image, the NoisePrint method, it automatically extracts a camera model fingerprint. And then this fingerprint, we can see, for example, here, 2 different regions. So this means that one region comes from a camera, which is not the same as the other region. And we can simply transform this NoisePrint into a heat map, which then clearly shows the region that was probably forged. So we have the NoisePrint method with some that exploits the camera-specific noise, but these are relatively weak traces. And also after this noise that happened in the camera, there is most of the time some JPEG compression going on. So this compression noise is an attack on the NoisePrint already. So what we thought is, why don't we use this compression noise as a fingerprint instead? And that's where the Comprint method comes in. So we get Comprint, an image forgery detection and localization method that uses compression fingerprints. And so the Comprint method basically works in a similar way as NoisePrint. When we have an image under an investigation, we transform that into a compression fingerprint, where we can, if there is a forgery, hopefully separate 2 regions in the fingerprint. For example, here, that can be transformed into a heat map that states where it's likely to be forged. So let's first look at the first part. How do we transform this image to a compression fingerprint? The thing here is, if we want to have the same comprint if the same compression happened, and we want to have a different comprint when a different compression happened. And this we can do using Siamese training. So in Siamese training, we, during training, feed a couple of patches to a CNN. And then the CNN will output a comprint, or 2 comprints in this case. And then it will compare the distance between those 2 comprints. And the thing is that if these 2 patches underwent the same compression, then we want the distance between these comprints to be small. We want the comprints to be the same. On the other hand, if we do a different compression in those 2 patches, then we want to have a large distance. So we want the comprints to be farly separated from each other. Okay, so that was the first step. Now the second step, how do we get a comprint into a heat map? This is done using the SpliceBuster algorithm, which is the same algorithm also used in the NoisePrint method. And what we do here is from a comprint, we do feature extraction. We get a bunch of different features out of there. And on those features, we apply expectation maximization to cluster the comprint into 2 regions, regions that probably underwent different compression. So we get the comprint as a full method. But now we saw that Comprint and NoisePrint, they are both interesting methods based on the same concepts. Can we not combine the strains of both methods? So we propose to do a fusion of these methods as well. So how does this work? Well, it's quite simple. We have an image, we create the Comprint from it, and we create the NoisePrint from it, and we combine those 2 into a single heat map. And more specifically, we do this by doing a feature extraction on both fingerprints, then concatenating them, doing expectation maximization on that. And then we get a heat map that is based on the fingerprint from both the compression and the camera model. So for the training of Comprint, we used the race dataset, which consists of a bunch of uncompressed images, which are not forced again. So these are only pristine images, which should do good for generalization. We did a random crop on them, and then we did a random JPEG compression on them with a different quality factor or with a different non-standard quantization table. We used the ones of Photoshop. So let's take a look at the evaluation. Does Comprint work? And we're more specifically interested in if it works in the wild. How well does it generalize? So first, I will show some cherry-picked examples. For example, here, which I already showed before, we have a face swap example, and we can clearly see a difference in the Comprint, and this is also highlighted in the heat map. We also did a splicing, as I've shown in an example before, and we can clearly see the outline of the shark. Also, a copy move example here, we simply copied the kite surfer from the same image, and we can clearly see that this lights up in the heat map. Also, a retouching example, we changed the pattern of the board, and we changed the upper part of the suit of the kite surfer, and also these clearly light up. We also used some bigger data sets, which I will go over some examples of. So we have the VIPP dataset, which was made specifically for detecting double JPEG compression artifacts. So of course, this will work quite well on the Comprint method, because it's also based on JPEG compression artifacts. So on the upper left, we have the image. On the upper right, we have the ground truth. And then in the bottom, we have the Comprint and the corresponding heat map. So here we can see that this works quite well. Then we have the DSO1 dataset, which is a dataset full of spliced images. But the thing here is that there is no recompression. So they're all PNG images, uncompressed PNG images, or not with a lossy compression step, at least. So for double JPEG compression methods might typically work worse on this data set, but Comprint, it does not work on double JPEG compression, but simply on a different compression step. So one compression step that is different can be detected as well. Then we have this face swap data set where we, as the name says, we do a face swap, which also we see that here it works okay. Then we have the IMD 2020 dataset, which consists of a bunch of images found on the internet. So this basically mimics in the wild circumstances quite well. And these are mostly Photoshop-like images. Then we also have the Open Forensics dataset, which is a huge dataset full of face swaps, also of multiple faces at the same time. So these cherry-picked examples show already that Comprint can handle a wide range of manipulations. But on average, we can look at these larger data sets. How well does it perform? We see the F1 score, which is a harmonic mean of the precision and the recall, which is a measure for the forgery localization. We see that the results vary over the different data sets, and there is still some room for improvement. Similarly, for forgery detection, where we calculated a UC score, we see that there's still room for improvement. So what are some difficulties for the Comprint method? Here we see that when there is a uniform area, for example, a completely white area from overexposition to light, we see that this clearly lights up in the Comprint and then also in the heat map, although these are obviously unwanted artifacts in there. So this is still something that future work should look at. Similarly, when there are multiple forgeries, for example, here we have two face swaps. These both can light up in the Comprint, but then when we transform it to a heat map, only one of them shows up. So that is because the heat map, it shows two clusters, while there might actually be more than two. So this is something to look at as well. Now let's take a look at what is the advantage of the fusion of the noise print and Comprint. So here we have the Comprint in orange, noise print in purple, and then the fusion on top. So we see that for the F1 score for forgery localization, the fusion actually performs better than both of those methods individually. And that is something for a cherry-picked example here that we can show as well. So if we have an image with a face swap in there, we see in the Comprint, the face swap, the face here lights up quite easily. But then actually, because of some other artifacts around, there are a bunch of false positives in the heat map. We get something similar in the noise print. Again, the face, it's quite visible here, but then in the heat map, it's also some other regions that are visible. Now, if we actually do the fusion, because we combine the powers of the two fingerprints, the face shows up much more clearly and there are less false positives. So in this case, the fusion performs better than the methods individually. For forgery detection, on the other hand, on average, Comprint performs slightly better, although the difference is very small. So, of course, all of these results, they have to be placed into context compared to the state of the art. So here we see from a bunch of different methods that we tested, the F1 scores for forgery localization. And at first sight, we see that the Comprint and the fusion, they perform quite well. They're on the top of all the methods. And we can basically divide these methods into the data-driven deep learning methods that I've mentioned before, and then the model-driven conventional methods. And more interestingly, we have some compression-based methods here at the bottom as well. So let's first compare our methods to those compression-based methods. We see that if we take the average of all data sets, we see that the ADQ method, for example, it performs similarly to Comprint. But on the other hand, if we take a look at only the DSO1 data set, we see that suddenly Comprint performs much better than ADQ. And also the DJPEG method suddenly performs better than the others. So why is this? Well, we saw that in DSO1, actually, the methods are that we used, they are trained with the Photoshop quantization tables, and in ADQ and other methods, they do not take these non-standard quantization tables into account. And we noticed similarly that if we train Comprint without these non-standard quantization tables, we also get a worse result. So this is a first interesting observation that we can make from the evaluation, that taking these non-standard quantization tables into account is quite important. The second thing that we noticed is that some state-of-the-art methods can have some generalization issues. For example, here on the Open Forensics data set, the MantraNet method, it performs very well, similarly to Comprint. But then on another data set, FaceSwap, suddenly it performs much worse than Comprint. And similarly, so this means there is a limited in-the-wild performance for this method. Similarly, the CRCNN method, it performs the best on the IMD 2020 dataset, the best of all the methods that we tested. But then on the Open Forensics dataset, suddenly it performs much worse than the others. So some state-of-the-art methods can have some generalization issues, especially when they are trained on specific forgeries. While if during the training we only look at pristine images, we have the advantage that this should generalize better than for those other methods. So when we look at the Comprint, individually, we have decent scores. We see that Comprint or the Fusion, it usually performs at the top of all the methods. Also for forgery detection, we usually are at the top of the list when we compare them to all the methods. And what we also see for forgery detection is that often state-of-the-art methods do not support forgery detection, or at least they did not include this in their proposal. So this is also something that they might need to look at. So in conclusion, what can we conclude from the evaluation? What are some interesting observations? So it's important to include non-standard quantization tables, for example, the popular ones of Photoshop. Some state-of-the-art methods have generalization issues, which Comprint has much less of it, but still Comprint can improve its performance. It's still not perfect, of course. But we saw that Comprint is a top-performing method in among the methods that we compare to. And also the Fusion is often better than the individual methods, Comprint or Noiseprint. So as such, the Comprint method that we proposed, it can already be used to localize and detect image manipulations. And we published the code of the method on GitHub, and it can be found on github.com/IDLab-MEDIA/Comprint. So this was the presentations. If you have any questions, you can ask them now, or you can send me an email or contact me through LinkedIn. And you can find more information about our research from both our group IDLab-MEDIA at Ghent University and the University of Naples, Federico II, on their websites listed here. Thank you.
Thank you, Hannes. Thank you. If your curiosity, Hannes, sorry, I don't, oh no. Yeah, it's just clapping hands. Denise, or do you have also questions for Hannes? You were clapping hands, I think. Oh, you also have a question. So yeah, you can go first, Denise. And also Anselmo.
Sorry, no, I wanted to confirm that I was showing the clapping sign. I'm sorry.
No, so no questions from your side? No problem. So Anselmo, do you want to start with your question?
Okay, so can you hear me?
Yeah.
Can hear me? Okay. So first of all, thank you for the presentation. So basically, I have some questions about your method in specific. So first of all, which kind of layer do you use in your Siamese network to find the comprint? So what would be the comprint in your architecture? So how do you really find the comprint to compare against other and say, look, they have the same compression. So how exactly is calculated this comprint in your Siamese network?
I had the same question. Thanks, Anselmo.
And another one is regarding the patches. So you put patches. So what is the methodology for you to select these patches? Because it seems that you will have a very unbalanced data set. So you have patches with the same, more pair of patches with the same compression than otherwise. So first of all, how do you calculate the comprint? And second, how do you select the patches to feed your network? Thank you.
Okay, So at first, we basically let the network figure out on its own how the comprint should look like, but we pre-train the network first to calculate the compression artifacts. So we basically do a compression artifact estimation at first, which we know the ground truth of that. And then from that, we start to do the comprint, which we simply just say they should be similar or they should be dissimilar depending on those couple of patches that we feed it. I think that is relatively clear. Then for the patches, indeed, we decided that 50% of the times the patches underwent the same compression and 50% of the times they underwent a different compression, and then we vary the quality factors or the quantization tables there. This was indeed chosen quite arbitrarily, this number 50%. We could have also done another percentage, but we noticed that this had decent results. We didn't really experiment much with other divisions of balance.
Okay, thank you.
Have you done some experiments just evaluating the performance with respect to the different resolution of the input image? Because of course, the one of the key points of the JPEG is the 8x8 block, no? But depending on the content of energy that you have in each block, the result could vary or not. Have you noticed some special behavior?
We have actually not tested specifically on that, no, indeed. So I don't think I can answer that question.
And did you find? Did you also run some experiment with social network shared images? Because this is another curiosity that I have.
Mm-hmm.
So some other processing can be applied to the image. Did you test it, or did you test?
No, we did not test on that yet. No, indeed.
Because I was curious to understand, because to some extent you say in few cases the fusion is working better, Comprint with Noiseprint. Although I mean Noiseprint, so the two networks are kind of, I mean, complex. I don't know a Comprint because you are presenting this now, but I know very well Noiseprint. So I was curious to understand if it's really worth combining those. And on the other side, I was also curious to understand, but I mean, for future, if these could improve or vice versa, could Noiseprint outperform Comprint on social network shared images, because it's not only observing JPEG traces somehow. So if you process again with the JPEG compression, maybe this is more robust, but just I mean, my idea.
Yeah, we simply noticed indeed that the fusion is interesting because the Comprint and Noiseprint can be complementary because they are based on different assumptions. So if one of the assumptions does not hold, then at least we have the other one that we can still try. So I showed a cherry-picked example where we really get a better result, but sometimes it's also just that one of the two has a good result and the other one doesn't. But then when we combine them, they simply have one of it picks the best of the two. Yeah. So on average, then we get a better performance.
Okay. Okay. Thanks, Hannes, again. So we are gonna talk with you if we have further questions and wait for next results on Comprint soon.
Great. Thank you.
Thank you.